Okay, good afternoon. Today we start again our series of astrophysical seminar from, say, Bologna area, even if everything is going to be remote for the next semester at least. Our first speaker of the season is Enrico Garaldi, who took the master degree in Bologna, working with Baldi and Moscardini, and then moved for the PhD in Bonn under the supervision of Cristiano Porciani, and he worked mainly on galaxy formation and reionization. And since 2 years, he moved to MPA in Garking as a postdoctoral fellow, and today will tell us specifically about a project on the generation of magnetic fields around the first galaxies. The talk is going to be recorded and later released over the YouTube channel of the observatory. And if you have to ask questions, please book yourself on the chat and we can do the Q&A at the end. Please, Enrico, the stage is yours.
Okay, thank you, Franco. Thank you all for being here. As Franco mentioned, my main research topic now is actually reionization, but soon you will understand, I hope, why I got interested into magnetic seeding and why I'm going to present today the impact that different magnetic seeding mechanisms have on galaxy formation. Let me just mention before jumping in that I've not been working on this project alone, but also aided by Rüdiger Packmore and Volker Springel, both here at MPA. Okay, let me just give a brief introduction what is the problem we are trying to solve. I'm sure you all know, but let me just mention that magnetic fields are basically everywhere in the nearby universe. Wherever we look, we kind of find magnetic fields, it seems. So we have them in galaxies. You can see on the left a nice spiral galaxy where you can see the magnetic field winding up along the arms of this galaxy, but also above and below the galactic disk. We do see actually magnetic fields. We see them in galaxy cluster. And on much smaller scale, we see in H2 regions around newborn stars, just ionizing the surrounding medium, or in supernova remnants, especially across the shock. And we are actually starting to see them also in the cosmic web. So recently, these cluster bridges so we have seen magnetic fields in cluster bridges. So, filaments connecting two clusters that were shown to be magnetized. And then I put a question mark in the IGM because there has been a claim of a lower limit on the magnetic fields in the IGM, but this has been heavily debated. So I would say this is still out to be determined if the IGM is magnetized or not, and to what level. But we have a problem, and the problem is that we don't exactly know where this magnetic field comes from. And for once, the problem is not that we don't have an explanation for their origin. We actually have two main explanations, or let's say we are like in a buffet where we have to pick one or pick what is the dominant mechanism, but we cannot make a decision. So listing all the seeding mechanisms that have been proposed would be too long. And so for the purpose of this talk, I've come up with three categories, three classes of this seeding mechanism. The first one is cosmological, what I call cosmological seeding, which in this case includes everything that happens at the CMB time or before that. And basically what matters here is that there is a small magnetic fields in basically all the gas in the universe before the beginning of a structure formation. Another possibilities are compact objects, for instance, stars or AGNs that can create and amplify magnetic fields and then eject them into the surrounding medium, for instance, when the stars explode as supernovae, or through IGN jets. And then there are plasma physics effects. For instance, the Biermann battery, which is the most famous one. So basically, effects that involve plasma processes. For instance, in the Biermann battery, the swirling motion of electrons and ions creates magnetic fields, and whenever you have a misalignment between temperature and density gradients, these magnetic fields have or at least part of these magnetic fields is coherent, so you obtain a large-scale magnetic field. Now, I would like to add a fourth one, which is actually the reason why I got interested into this issue, which is the production of magnetic fields through basically photoionization. So during cosmic ionization, when the ionization fronts from the first galaxies were sweeping through the intergalactic medium. So let me just mention how this works. It's pretty simple. Imagine you have your neutral hydrogen atom being hit by a high energy photon that is basically ionizing this atom. What happens is that the photon transfers its momentum to the proton and the electron in roughly equal amounts. But given the very different mass of these two particles, what happens is that the electron travels much farther away than the proton, and so you create an electric field. Now, if the source of photons is, or if the photon flux is somewhat coherent, you basically get a coherent electric field. One example of this is the ionization front around, as I said, the first sources of photons. In this example, however, the electric field has a vanishing curve, and so the magnetic field is again 0, but you can imagine that inhomogeneities in the intergalactic medium or in the distribution of matter can easily bend the ionization front and so create a locally non-zero magnetic field. That can be simulated, for instance, as I'm showing here. So what you see on the bottom right is an idealized simulation I ran with the repo code, where I just placed a Gaussian over density in gas. You can see this in the central panel. And what I call a galaxy, which in this case just has a power law spectrum for the radiation, and then just let the ionization front of this galaxy sweep through the overdensity. And you can see on the right-hand side that there is a small magnetic field, coherent magnetic field that has been produced. Okay, so we can add this fourth mechanism that for short I will call the Reeve battery, as the Biermann battery explained before. And yeah, let me just mention before moving on that we now have we have many different ways to produce magnetic fields. What is relevant, what is important though, is are also galactic processes that can and will amplify and then eject magnetic fields into the surrounding medium. So if we really want to study the impact of these magnetic fields, we want to have a good galaxy formation model. For that, I turn to the Auriga galaxy formation model. This is very similar to the illustrious TNG one, and has been built specifically to simulate Milky Way-like galaxies. It's based on the repo moving mesh code and solves the ideal magneto-hydrodynamical equation, to which I added the radiation transport solver coupled to this MHD equation. And on top of all the physical modules, physical processes included, stellar winds, stellar ejection from stars and supernovae, black holes, and so on, I've also included a variable seeding mechanism. In particular, as I mentioned, I have a cosmological seeding where we just inject a 10 to the minus 14 Gauss field in the initial conditions with the simplest geometry possible, aligned with one of the axis of the simulation box, and then wrapped around thanks to the periodic boundary conditions. I've included a very simple model for the injection of magnetic fields from supernovae. Basically, 0.01% of each supernova energy is injected into the dipolar magnetic field, randomly oriented and centered on the supernova explosion position. And then we self-consistently solve the Biermann battery and this Reeve battery equation. And then we run both Zoomin simulation focusing on individual galaxies. You can see on the right-hand side a sample of galaxies from the Auriga project. And then we also run cosmological boxes where the resolution is just initially equally distributed across the entire box. So we can basically simulate an entire population of galaxies, although at a lower resolution. Okay, let me start from the first set of simulation, the Zoomin ones, that can allow us to tell something about subgalactic scales. So as mandatory for every simulation talk, let me start with a movie. What you're gonna see are 3 slices through the simulation box. These are the top panels and the bottom left one. On the top left, sorry, you see the gas over density evolution. The top right is the magnetic field strength, and the bottom left is the metallicity. And on the bottom right, you will see the radial profile of magnetic field strength around the main galaxy that we simulate. Each of the slices is actually divided in 4 quadrants, as you can see, and each of the 4 quadrants will show a different seeding mechanism. So let me just play this, and I will play it again afterward because there is a lot to be seen here. So if you focus on the top left panel, you can see that we just have the usual collapse of gas, and you can see there is no discontinuity when moving from one quadrant to the other. So this is telling you already that the galaxy itself is not really affected. The gas dynamic is not really affected by the magnetic seeding process. And the same actually goes for the metallicity. Let me just play this again. And if you now focus on the top right panel, you will see that the magnetic field is injected and is amplified at very different times, and so ends up with very different geometries in the 4 different models. And this is true until basically redshift 1 point something. But after that redshift, all the memory of the initial field has been erased. And this can be seen also in the bottom right panel, where basically out to the largest distance we can probe with this Zoomin simulation, the magnetic field's strength profile are indistinguishable. To be a bit more quantitative, I've plotted here the volume average magnetic field strength within 3 different radii, 1, 10, and 100 physical kpc from the center of the main galaxy. And so you can see, well, there are a couple of things to be seen. The first one is that once the saturation level is reached, so the right-hand side of this plot, the magnetic field strength is basically the same in all models. So there is no memory there of the magnetic field seed, and this is also consistent with observed magnetic fields in Milky Way type galaxies. Another thing to be noticed is on the left-hand side of the plot, and the fact that different seeding mechanisms inject very different strength of magnetic, well, the strength of the magnetic field they inject is very different, and so also their saturation time is not the same. In particular, you can see that when we inject magnetic fields from supernovae, this is the most, we inject the largest field, and so this reaches saturation much earlier. However, there is a caveat, and the caveat is that even this Zoomin simulation cannot fully capture all the turbulent dynamics in the galaxies, and so we are basically underestimating the dynamo effects at play within galaxies. And so the time at which saturation is reached will depend on resolution. The relative ordering of this will not, but you can see here in the bottom right that if we run the same simulation at higher resolution, we actually reach saturation earlier on. Okay, so I won't go through all the different analyses we did on the galaxies, but I'm trying to convey one message, which is that the galaxy itself is not affected by the seeding mechanism. This doesn't necessarily mean that the magnetic fields have no impact on the galaxy, just that all these different mechanisms we tested have a very similar effect on the galaxy. So what you see here is just a collection of some quantities in simulation with different seeding mechanism. And so you are looking at the virial radius and mass, and the half mass stellar radius and mass. And you don't need to really look carefully at the numbers. The message is just they seem to be insensitive to the seeding mechanism. And so now I hope to have convinced you that galaxies, well, in all these seeding mechanisms, galaxies can actually amplify the original seed to levels as seen today in observation. And so we would like to know what happens outside of galaxies. And to do so, we run some cosmological simulations where we are forced to lower the resolution within individual objects, but we can then study entire galaxy populations. So again, a movie, this is exactly the same as before, except that the bottom right panel now shows the temperature of the gas. And I should mention that we have used the same setup as the Zoomin for consistency, although, as I mentioned, the Auriga model was built to simulate Milky Way-like systems. But again, it's similar to the elasticity in G that has done so well on large scales. So we are pretty confident this is working also on large scales. Okay, let me play the movie, and so you can see that the gas is collapsing as usual and heating up the IgM during ionization, and then you have the production of metals. This is all going on as usual, no surprises there. But when we look at the magnetic field strength on the top right, you can see that the different models have a very different, rather predict a very different strength of the magnetic fields in halos. So we can actually have a look at that a bit more closely. And so what I'm showing here is the volume average magnetic field strength within halos as a function of the halo mass. Okay, there are quite few things that one can take away from this plot. The first one is, again, that once the fields reach saturation, so the right-hand side of each panel, there is no memory of the original field. And this actually, the saturation level is the same again for all the halos, for all the halo masses. If you now focus on the left-hand side of this plot, you can see that the supernova injection scheme seems to behave a little different from the other three. So the reason is that in the supernova injection scheme, the seed itself is pretty strong and localized within galaxies. So it's very easy for the galaxy to amplify this initial seed because it's already in place where the amplification takes place. And so basically everything which is not saturated there is because it's made up of gas that has been ejected by object where the field has reached saturation, and then because of flux conservation has been diluted and then maybe reaccreted into other objects. Indeed, below 10 to the 10.5 or so in virial masses, our halos have only a handful of stars, and so these are halos that are really at the resolution limit. However, you will see that in the other three panels, there is instead a pretty clear trend of increasing magnetic field strength with halo mass. This is consistent also with previous simulations. And what is interesting is that the mass threshold at which this curve converges to the saturated value is actually different for different seeding mechanisms. And again, this is just a consequence of the different strengths of the original magnetic field. So we can have a look at the same plot, but now for the entire gas in the simulation, which will tell us more about what happens outside of the galaxies. Oh, sorry, I should mention there are also stars, star symbol in this plot that are very hard to see, and this is actually good because the star indicates where in this plot the Zoomin run ends up, and the fact that it's hard to tell where these stars are means that these simulations are very well converged. So even lowering the resolution doesn't really change the result. Okay, so this is basically the same plot, but now we are looking at all the gas cells in the simulation. You can see that for most of these mechanism, again, the Duriv and Biermann battery and the cosmological injection, the low density gas and the high density gas seems to follow both this magnetic field strength density relation, which is just due to flux conservation in ideal magneto-hydrodynamic. And then there is a transition region that just shows you where the gas is being amplified. The magnetic field is being amplified. What I want to point out is that if we take this Neronov and Vogt lower limits on the magnetic field strength, which again, as I mentioned at the beginning, these have been debated. If we take them at face value, though, this indicates that the Biermann battery and the Duriv battery are actually not sufficient to explain the observed level of magnetization in the IgM. And this, we believe this should be pretty strong with resolution, because in the IgM, the resolution, the main effect of increased resolution is to render the amplification more efficient, but the field in the IgM mostly depends on the ejection mechanism of gas from galaxies. So there should be, nevertheless, a some small trend with resolution, but this should be much stronger than the result I showed you at the beginning. Okay, finally, I want to show you that we can also produce rotation measure predictions. So I will ask you to focus on the right-hand side for now. Each row is showing a different redshift, and each column is shown a different injection mechanism. And so you are just seeing a map of the rotation measure computed, basically projecting the simulation along one of the axes. So you can see, even by eye, that these maps are very different. In particular, even at redshift 0, where we can observe these rotation measures in the real universe, these appear very different. In particular, the supernova injection, which is the leftmost column, has many more regions of high rotation measure than the Duriv or Biermann battery.
20 minutes.
Okay, thank you. Yes, I'm almost done. However, if you look at the insets, these are showing the rotation measure around the biggest halo in the simulation at that redshift. And so you can see, for example, again, looking at the bottom row, that these are all pretty similar. And indeed, if you just take these halos and plot the rotation measure as a function of projected distance from the center, you obtain what is shown on the left-hand side of the slide. The shaded region, again, is this distribution of rotation measures as a function of projected distance, and then the blue points are a collection of observations. And you can see that basically in all 4 different seeding models, well, they produce very similar rotation measure. And so although there are differences that may be one day observable, current observation seems not to be able to constrain different seeding mechanism yet. Okay, with this, I'm actually done. Let me just mention 2 of these takeaway points. The first one is that the observed galactic magnetic field can actually be explained without a cosmological seeding. And this may be straightforward for someone, but indeed, a cosmological injection is what is used most of the time in many of the galaxy formation simulations. And so I think these results may raise the point that we can use a more physically motivated prescription for magnetic fields in this kind of simulation. Although I'm obviously open to discuss this point with everyone. The second point I want to make is that the Duriv and Biermann battery mechanism actually behave very similarly, both in their spatial distribution and the strength of in the spatial distribution, but the Duriv battery injects a field seed strength which is systematically lower than the Biermann one. And so I think in a realistic scenario where both of them are actually active, the former is almost always subdominant. Okay, with this I'm done. I thank you all and take questions.
Okay. Thanks. So I don't see, let me see, I don't see questions there. So I think I can start. So, who's speaking, sorry?
Carlo.
Okay, bye, Carlo.
So Carlo wants to ask a question. So Enrico, at some point you have shown that in the simulation of the isolated systems, so below redshift 1, so you basically wash out all the information about the initial magnetic field that you have in the simulation. But if you go to the next slide, no? If you go to the next slide, the one where you show the correlation between the magnetic field and the mass of the halo.
This one?
Yes, this one. So,
okay.
So basically, I was thinking that the magnetic field became basically saturated. No, so you basically wash out the information about initial condition when the halo collapse. No, at some point, and basically, I expect the small systems to collapse at high redshift respect to the largest systems, and I expect for the small systems basically to have reach this saturation level of the magnetic field. So I was wondering, so how much these results that you have here is solid or could be dependent on the resolution of the simulation or what?
So I think it's definitely true that small systems collapse at higher redshift, but I think larger systems are just more efficient in amplifying these magnetic fields. I mean, because what you need really is not, so flux compression is not enough to reach saturation. You really need dynamo effects, and these are mostly driven by turbulence. And so, at least in these simulations, and you just have more of that into high mass systems. Regarding like the how much converged these are, I think everything on the right-hand side is totally is fine. This has been studied also by Rudiger Packmore extensively for the Auriga simulation suite. What is not converged, I think, is maybe the left-hand side of this plot where we are really approaching the resolution limit. And so I expect there things may change, although qualitatively they should remain, the results should be similar. So probably this threshold mass, the position of this threshold mass will change a bit with higher resolution. But again, as I said, the differences between the individual models will always be there. And for instance, if you look at the bottom right panel, which has this cosmological injection, this is exactly the same model used for the Illustris TNG suite, and they recover the same result. I mean, I'm not sure if Federico is connected, but well, he definitely knows better than me. But I think they recover the same result, although the resolution is definitely much higher. I hope
Thank
that
you.
answer your question. Okay.
Thank you.
Okay. Anybody else? Otherwise, I can have a couple. Meanwhile, so one is when you have to compare with the lower limits by Neronov and collaborator, those usually are referred to high redshift blazars, right? So redshift, I don't know, larger than probably 0.5, 0.6, something like that. So the phase diagrams you are showing here are, I guess, for redshift 0.
Yes, sorry, I forgot to mention. These are redshift 0. Yes.
So because I'm not super familiar, but I guess the limit they give you is some sort of convolution for redshift. So I wonder if the same model would have a much lower volume filling factor at higher redshift, if there is still a way for some of these models to be compatible with the Neronov limits, because most of the effect, I guess, would be coming from close to the source. So the lack of the inverse Compton cascade would be probing magnetic fields. I don't know exactly if it is more close to the source or it's the average, but anyway, if your volume filling factor is a strong function with redshift going towards redshift 1, I was wondering if there is some room still for those observations to be, I mean, for your simulation to be compatible with that.
So I'm also not, so we haven't done a full synthetic observation of the simulation. So I can, there's still maybe room for little changes, but I think, so I'm showing redshift 0, but I've checked the same plots also at higher redshift, and the situation actually doesn't improve that much compared to this lower limit, in the sense that for this Duriv and Biermann battery, they are still pretty, it's pretty hard to recover this limit. As you can see here, I mean, most of the gas has a much lower magnetic field strength, and that's not changing much at redshift 0.5 or even 1.
Okay. So your conclusion would be there must be something else. If you believe the limits, say there must be.
Yes, I think that would be my conclusion. Although again, as I said, I mean that's not my main topic of research. So I'm just coming to this now. So I'm very open to suggestion sure. In any way to discuss this. But yeah, that's my conclusion now. Again, the only thing is, again, I haven't produced like synthetic observation of this. So I'm trying to include all the possible effect in this inverse Compton cascade. So yeah, there may yeah, unless there is something really weird, strange going on there, my conclusion would be yes, that one.
Okay. And the other is the saturation level you are reaching in all models. If it's a dynamo, I think it should be anchored to some level of equipartition with respect to the kinetic energy of the galaxy, I guess. Otherwise, I mean, do you have an what is this level? Is it 1%, 10%? What are you getting?
Yeah, okay. So this is close to 10% equipartition in the models. Yeah, to go beyond that, you need some kind of basically galactic dynamo that can boost you above that level. But again, this is not happening, or it's happening to very low levels in the cosmological run just because of resolution, probably.
Because in the Milky Way, we are a factor of a few larger than this, I guess. We are more closer to, okay. So you say is the large-scale dynamo that we miss there. Okay.
Yes. At least this is also, I mean, this is what I found in my simulation, but this is, again, that's what happens in basically the entire Auriga suite, which uses this cosmological injection. So I'm pretty confident this is what's happening.
Okay, makes sense. Any more questions for Enrico? I don't see any. Okay, so I think that's it for today. Thank you. And let me stop the recording.